Hey guys, this is our last section for 7.4.3. Just a heads up of where we're at right now. We're on this day 3 of week 3-2. You're going to have a review period day 1 next week, and then your test, which is 7.3 to 7.4 only. That's only material covered in this, on this packet, is day 2 next week. Okay? So last lesson today, review next period, and then test day 2 next week. All right, let's get into it. Last section, linear programming. Linear programming, a method used often in business and economics that attempts to maximize or minimize a linear function over a set of feasible solutions, a region constrained by a system of inequalities. For example, I'm trying to maximize for profit. I get $100 for every x and $120 for every y. My profit function is p equals 100x plus 120y. Under the two lines lies the feasible solutions. So these are constraints. These two lines here, these are called constraints. And those will be either given to you or you'll write them out from a word problem, and I'll go over that in a couple pages. And generally, it depends what your constraints are. But for this example, let's say that your feasible region is right here. So we're saying that whatever needs to be true needs to be less than this and less than this. Okay, so it must be this region. How do I maximize our profit? So the steps to solve these problems are you look at your profit function, you get your constraints, which are either given to you or you'll write them out, and then your maximal profits or your minimum profits are going to be at one of the vertex or corner points of the feasible region. So here, 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 and here are all possible optimal points. Okay? Does that make sense? So within the feasible region, the corner points are what you care about. So once you have your shaded region, you're going to test those points. So what do we have here? Well, we have We have 0, 0, right? That's 1 point. That's right here. We have 0, 15 up there. We've got 10, 10 right there. And then we've got 15, 16, 17, 18, 0 there. Okay? And so we're going to plug in these coordinates into that original profit function, 100x plus 120y. Just for clarity, this profit function is not one of the constraints, right? It could be part of one of them, but unless it tells you that, this is not part of your constraints. Okay, so let's put them in. So if I put 0, 0 into that above, we're just going to get 0. If I put a 0 and then a 15, I'm going to get 1800. If I put a 10 and a 10, I'm going to get 2200. If I get 18 and 0, I'm going to get 1800. Right? So what's the best out of those? This one right here. So 10, 10, 10 of x and 10 of y. This would be your optimal solution. Okay? Follow me? We're going to do 2 more examples, building in difficulty. Example 2 is a bit more fleshed out. And these are the steps that you want to follow right here. So we're defining our objective function. What are we trying to maximize or minimize? We're defining our constraint functions, which are the inequalities. We're graphing. We're finding the vertices, and then we're testing the vertices. So this is not a word problem, but the objective function and the constraints are given to us. This is the objective right here. These are my constraints. Let's graph it. Okay? So if you're graphing this without a graphing calculator, you just want to get y alone in these top 2 equations, right? Y is going to be less than or equal to negative 2x plus 10. And then y would be less than or equal to negative 2/3 x plus 14 over 3. We also know that x is greater than or equal to 0, and y is greater than or equal to 0. So these two right here tell us what? They tell us that we're going to be in this first quadrant right here because y has to be positive and x has to be positive. So I'm limited to this already. Then I've got these two. Let's graph these. So we have negative 2x plus 10. So we start at 10, and then we're going to go over 1 down 2. Get the 2x. Okay. Right, it's roughly like this. And then we have negative 2/3 plus 14 over 3. So 14 over 3, that's 4.6, so starting right here. And our slope is negative 2/3. So I'm actually going to intersect right here at 1, 4 will be a point here. 1, 4 will be a point. And I can keep going. It's going to go over 3 down 2, just like that. Oop. And we'll have this line here. And this says I want to be less than this and less than this. So I want to be below this one and below this one together. And the only region where that's true is this quadrant here. So this is my feasible region. Okay? Then we need to get those vertex points. So my vertex points, or vertices, would be, well, we got 0, 0, right? We've got 5, 0, and we've got 0, 4 and 2/3. Okay? Those are my, oh, and we've got 4, 2. Okay? So you've got these four points here. 1, 2, 3, 4. Let's plug them in. So again, when we plug them back into the objective equation up here, 5x plus 8y. Right, so this goes into 5x plus 8y. Well, when 0 and 0 go into that, you're just going to get 0. Right, that's probably going to be our minimum. For 5 and 0, we're just going to get 25. For 0 and 2/3, 4 and 2/3 rather, you're going to get 37.3. And for 4 and 2, you're going to get 36. So it would say that 0, 0, this would be our minimum. And then 0, 4 and 2/3 would be our maximum. Okay. All right, we'll do one more with a word problem. And again, just cover the steps one more time. You've got your objective function, you've got your constraints, you graph your constraints, you shade the goal region, you find the vertices, you test the vertices into that objective equation, and then you're either choosing usually either the minimum or the maximum, and it'll tell you in the question. All right, last problem, real world problem. This is in the book number 7. Senior's produce is purchasing fertilizer with 2 nutrients. We're going to read this twice. N for nitrogen and P for phosphorus. It needs at least 180 units of N and 90 units of P. Its supplier sells 2 brands of fertilizer. Brand A costs $10 a bag and has 4 units of N and 1 unit of P. Brand B costs $5 per bag and has 1 unit of each nutrient. Sanger's produce can pay at most $800 for the fertilizer. How many of each brand should be purchased to minimize total cost? Okay, so there's a lot of information here. I think a good place to start is actually the last part of the question. How many of each brand should be purchased to minimize total cost? That's our goal. Like, this is what we want to answer. So let's say that X is going to represent bags of brand A, and Y is bags of brand B. Okay? How many of each should be purchased to minimize total cost? But we have these constraints above. So let's get our objective function first. This is going to be cost. Well, how much do each of these bags cost? Well, we know that X costs, which is brand A, is $10 a bag. And we know that Y, which is brand B, is $5 a bag. So it would be, cost would be 10X plus 5Y. Make sense? It's $10 for bag X, $5 per bag Y. Just add them together. Constraints. Well, you can't have negative bags. So some basic constraints that we can put are that the X must be greater than 0 for both, and the Y must be greater or equal than 0, right? So both bags, we can't have negative bags. It's got to be 0 or higher, right? So I mean, that's given to us kind of by this quadrant here. We're not given the other quadrants. We're only dealing with this first quadrant. Okay, what else? Well, we have these constraints around nutrients. We need at least 180 units of N and 90 units of P. So I'm probably going to have to use them somehow. So I'm going to go ahead and just write we have 90 and 180. Okay, so these are going to be involved somehow. So whenever you write your equations, you need to make sure that the units are the same on both sides. So, but I want to keep using X and Y. I'm not going to introduce P and N. I'm going to keep using X and Y. But I want whatever, this is 90 units of P, right? And this is 180 units of N. I want the left side to kind of be in units of P, right? So I want at least this much. So I need 90 or greater. I need 180 or greater. And over here on the left, well, how much, remember this is P. How much P does, how many units of P does bag A have? Well, it has 1 unit of P. And bag B also has 1 unit of P. So that would say that X plus Y has to be greater than or equal to 90. This is also like just telling me P. Okay? Below, this is N. This is a little bit different because bag A has 4 units of N. That means when I write out X, and you write 4X, because I need to show that it's got 4 units of N, not 1. Okay? And the last one here is that it can only pay 800 for fertilizer, at most 800. So that means that I cannot pay more than that. So if this is in dollars, on the right, on the left hand side, I also need to write it in terms of dollars. So how much do these cost? The same as the cost equation over there. 10x plus 5y must be less than or equal to 800. Okay? These are my constraints. Now let's plot them. Okay? So when I rewrite these, get y alone, I'm going to get that y is greater than or equal to 90 minus x, y is greater than or equal to 180 minus 4x, and y is less than or equal to negative 2x plus 160. That's just isolating y for all of these. Okay? Now let's plot them. Okay, so 90 minus x would be starting here at 90, and it would just be over 1, down 1, so just like this. Okay, and then 180 minus 4x would be starting here at 180. It would be over 1, down 4. 1, 1, 2, 3, 4, this. And then 160 minus 2x would be starting here and going down 2. Okay, roughly like this. Okay? All right. So now this might be like, my lines might be a tiny bit off, right? They might not be completely perfect, but it's roughly correct. Okay. What's the region I want to shave? So you have to look here to the right. I want to be above 90 minus x. So 90 minus x is, so I got to be above this. I want to be above 180 minus 4x. That's this one right here. So I got to be above here. But I want to be below negative 2x plus 160, which is right there. So the overlap of all those regions is this triangle here. Okay? Got it? So again, we read our question. From that, we got our costs and our constraints. We got y alone. We plotted them. We shaded based on our inequalities here. Now we got to get our vertices. So these points are 10, 140. This is 70, 20. And this is 30, 60. How did I get those? Well, my graph isn't perfect, and it's may not get me like these exact numbers. A way that you can confirm what they are is by putting them in your calculator, right? And by using second trace intersect, right? So in your calculator, second trace intersect, right? That will get you the correct values here. All right? Now we're going to test the points. So we have 10, 140, 70, 20, and 30, 60. And we're going to plug those into our original, the master equation, the objective equation, 10x plus 5y. 10x plus 5y. Okay, we plug them in, we're going to get 800, 800, and 600. Remember, the question is asking for the minimum, so this would be my minimum. So 30, 60 would minimize costs, and that's your answer. Okay? So feel free to watch this video back and forth as many times as you want. Just to clarify the graphing calculator problems, you're going to be allowed to use a graphing calculator, but you still need to show all the work just like this. Okay? So bear that in mind. You can use it to help you find the intersection points, but you need to be able to show your work just like this. Okay? Also, for the homework, 2 parts, like before. We got the delta and then there's the textbook problems, like 3 textbook problems. So don't forget to do both. Okay? All right, guys, have a great class, have a great day, have a great weekend, and I'll see you next time.